Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to try to bring all of our ideas for this chapter together in complex sinusoids. So the last little bit that I need to introduce, or maybe even draw together more closely, was this: is that we said if you had the number z, you could write it as r times cosine, or I'm sorry, let me go back. You could write this as r times e to the I. You could use t or theta. We'll use a t this time. And that is the same as r times the cosine of theta plus plus I times the sine of theta. And you can distribute the r, and you can say this is r cosine of theta plus I times r sine of theta. Now, let's do one more thing. Let's remember that a real number, a complex number, has two components, a real and an imaginary component. So I could say, for example, that the real part of z is equal to r cosine of theta. And the imaginary component of z is the sine, I forgot my r sine of theta. Okay. It's with this that we can put together all of the pieces of our puzzle. And we're going to do that today, and we're going to finish it with an example. Here we go. Got to take a big deep breath for this. This is a lot. Where did we start? We started this problem with y prime equals a y plus some input q. And in this problem, in this section, we're studying the sinusoidal input. So we said this is y prime equals ay plus a cosine of omega t plus b times the sine of omega t. But then we went one step further and we said, well, a cosine omega t plus b sine of omega t, there's this interesting relationship that you can rewrite this as you can rewrite this, I'll do it this way, as y prime equals a times y plus r times the cosine of omega t minus phi. And the parts here was the parts we found out was that r is equal to the square root of a squared plus b squared. And it came from, and phi is this, I'll do it here. Phi is this triangle that looks about like that. And it has an angle phi inside, and then it has your adjacent side is A, and your opposite side is B. And so from that, then we could also say that the tangent of phi is B over A. In other words, phi is the arctangent or tangent inverse of whatever B over A produces. Okay, so that took us to this step here. Okay, now we're going to go one step further, and that's what we just started with. But look at what we just said. If we have the complex numbers, so what I want to do is think of this equation now as a complex equation. And just so that we keep in mind that it's complex, I'm going to put a little tilde over all of my y's, because now we're going to take a look at the complex equation, y tilde prime equals a y tilde plus, we said now that we can rewrite this as r times e to the I omega t minus phi. That's what we just found out. We found, and what this is where r cosine omega t minus phi equals, it's the real component of e to the I omega, whoops, let me write that, I omega t minus phi. And if you still struggle, we can expand this. It's the real component of, if we can expand this is cosine. Oh, whoops, I forgot my capital R in there. Capital R. It's the real part of capital R times cosine omega t minus phi plus plus I r sine omega t minus phi. There it is. So now, in other words, we can just solve this complex equation and we should have our answer. Well, remember, we already did. We solved this. So we said, okay, our particular solution is going to be of this form y e I omega t. And then what we found out is what y was. Is that, oops, let's write it this way. We found out that capital Y is equal to r divided by I omega minus a times e to the I omega t. And that's where we are. How do we put this all together? And I think the best way to see this, is through, and actually this should probably be a tilde now, is through an example. So what we're going to do is we're going to solve y prime, let's see here, minus y, or let's do this, equals y plus cosine of t minus the sine of t. Okay, and what we're going to do is we're just going to use all of these relations that we've found. And what we're going to do is just solve this for y particular. Okay, well, how do we do that? Well, look at what we do. We just follow these steps. In other words, I'm going to write this as y prime minus y is equal to the cosine of t minus the sine of t. Okay, but now we want to write cosine of t minus sine of t as just cosine. Well, we can do that because look at this. In this case, a is 1 and b is negative 1. So let's graph that. That's going to give us this triangle where a is 1. That's my horizontal component. And my vertical component is b. Let me make it a little, let me undo that. So I did not exactly to scale, but pretty close. So here's 1, here's negative 1. This is my angle phi inside of there. That's my angle phi inside of there. So look at what we have. We have r is the square root of each side, so 1 squared plus 1 squared. So r is the square root of 2. And look at this. And the tangent of phi is the opposite, minus 1 over 1. Well, this would imply that phi, I'm going to need some space here, so this gives me that phi is minus pi over 4. So what can I do? In other words, a differential equation now is y prime minus y is equal to r, so the square root of 2 times the cosine of omega, in this case is just 1, I'll write that, 1t, minus now our phi angle, which is negative pi over 4, so minus pi over 4. And we'll clean that up in our next step, or I'll do it right now. So this is really just the square root of 2 times the cosine of t plus pi over 4. Okay, we're going to take that, put it onto our next screen, and find this solution using what we have discovered. Copy, go here. Now, let's think about our next step. So really, we're working with this problem of y prime minus y is equal to the square root of 2 times the cosine of t plus pi over 4. And now, remember what we said. This is the capital O. We can go one more step. Now, if we think about our complex solution, we have y tilde prime minus y tilde. Well, this is equal to the square root of 2 times e raised to the I of t plus pi over 4. Oh my, we're almost done now, because we already know this solution too. Remember what we said. We said that now our y particular is going to be capital R, which in this case is square root of 2, over I omega minus a times whatever our e piece is, which is I t plus pi over 4. Well, if we continue this out, in our case, omega is just 1. And our A is 1. And so what do we have? So we have that we can rewrite this. Oh, so now let's rewrite, I omega minus a, which is I times omega, that's just 1, so it's I. A is 1, so minus 1 in polar form. Okay, well, let's see. Our length of this, the length of I minus 1, this is just going to be the square root of 1 squared plus 1 squared. And I'll and well, let's just draw this picture. I minus 1 looks like this. So it's up, so up and over. So it looks like this. Okay, here's my real axis, my imaginary axis. And so then if we go minus 1 and then up 1, so my rectangular coordinates would look like this. And now we'll call this angle here alpha. Well, so you can see that the length is each side. Here's my opposite side is 1, and this side is negative 1. So, oops, I should probably use negative 1 in here. So plus negative 1 squared. Okay, well, what does this give us? This gives us now we have the square root of 2, and we also know this. We know that the tangent of alpha is equal to the opposite over the adjacent. And you can see what alpha in this case is going to be 3 pi over 4. So in polar form, what we have is that I minus 1 is equal to the square root of 2 I 3 pi over 4. I know this is a lot to digest, but bear with me because we're almost done. So now look at what we're going to do. We're going to put this into our solution over here. Okay, so let's rewrite this. I'm going to start back with this equation here. So now we know our y particular. Our y particular is the square root of 2 e I t plus pi over 4 over, well, we just found out that the denominator can be written instead as the square root of 2 e I 3 pi over 4. Well, when we clean that up, the square root of 2's will cancel, and then I just subtract the exponent. So this just becomes 1 times e I. Then I have I'll write it all out and then we'll clean it up for a couple steps. So I have t plus pi over 4 minus 3 pi over 4. So in other words, our particular solution is e I to the t minus pi over 2. Now, this is our complex. And what we want, though, is our actual solution is the real part of our complex particular solution. So let's do this. Let's remember, so if the complex particular solution is e I t minus pi over 2, well, this is the same as the cosine of t minus pi over 2 plus I times the sine of t minus pi over 2. And the real part, so then the real part of y particular, the complex solution, is the cosine of t minus pi over 2. But let's see what this equals. Remember, if we use the cosine, the sum of an angle's formula, this becomes the cosine of t plus, I'm going to come down a line here. So this is equal to the cosine of t cosine of pi over 2 plus the sine of t times the sine of pi over 2. Well, the cosine of pi over 2 is 0, plus the sine of pi over 2 is 1, so this just gives me the sine of t. So in other words, y particular equals the sine of t. And I know we've done a lot of work to come up with that. And yes, you could have gotten the exact same answer if you just used our original method of undetermined coefficients. But that's not the point. The point is to teach you how we can also expand our possibilities once we have the complex numbers, and we will be needing those shortly for some more solutions and more differential equations that we will encounter. I hope that helps. Thanks for watching.